Commencing film 2 for Newman Projections. These Newman Projections are shapes, different shapes or conformations or shapes of a molecule, which comes about because these molecules of interest have single bonds, which can be spinned or rotated. So single bonds with free rotation can be rotated. And these rotations give different shapes of a molecule. Certain shapes are more stable than other shapes. So we were discussing the spoke carbon, which is nearest to you, and the sphere carbon, which is furthest away. This is a nice design for a handout. We'll just be looking at this molecule here to the left. Again, we have this stick person standing to the left. The stick person is 6 feet tall, let us say, and then the molecule has been blown up to that it is 6 feet tall or as well, or something like that. So here we have hydrogen, hydroxyl, HHOH, T-butyl, methyl, methyl, T-butyl, methyl, methyl. And in this design, I will try to draw for you that this is I just drew an arrow to the, what I'm going to type here, the spoke carbon nearest to the person. And this arrow is to the sphere carbon, which is furthest away from the person, sphere carbon. So you see here, if you will, you have the spoke can be either like the letter Y, that is to say 2 up and 1 down, or it can be an inverted Y, that is to say 1 up or 2 down. We'll find out. And the sphere can be 2 pegs up, 1 peg down, or 1 peg up, 2 pegs down. So we'll find out, and we'll convert. I'm just going to do the molecule on the left at that point of view. And I may assign the molecule on the right for any homework that's necessary. So we kind of have it easy here, I guess, right? Because we have 2 hydrogens. One's on a wedge, one's on a hash. So it's they're both up. And so this is not applicable because we don't have to choose. So that's nice. Up. But I hope I put a lot of effort into making that clear. I took off my glasses and everything to try to give you a nice diagram on ChemDraw with the blue laser. I went to great extents to help you understand from points of view for wedges and hashes, what's left and what's right. So I hope you retain that. That's important. So we just lucked out here. The hydroxyl is more down, and this is also not applicable because it's straight down. How about T-butyl? The T-butyl was almost above the person's head, so we'll say that that's up, up. And again, turns out this is all not applicable, and the methyls are more toward the person's feet, so we'll say that they are down. And this choice of up, down will help us determine which spoke to pick and which sphere to pick. So for lasso this here, this is our spoke, is it not? Isn't this the spoke, HHOH? Okay. The spoke is up, up, down. Here we have down, down, up. That's not us. This is up, up, down. That's us. So I'll just plant the H's here. Up, H up. That's what I need. Table says it. H up. That's what I need. Table says it. And OH straight down. Partial credit is building. And the ones I did not circle above, those are the spheres. And we have up, down, down. Up, down, down. That's our pattern we want to fulfill. Up, down, down. That's it. Up, down, down. And fill it in, please, with T-butyl going up. And methyl going down. If you're wise to it, you can just leave these blank and they become methyl groups by default. Now, if I simply just superimpose the spoke and the sphere on top of each other, there you go. Now you have it. So I'll just do that. So when I do this, I kind of out of habit, I draw the sphere first. I just kind of draw that first. And what will not always, what we're drawing is another staggered conformation. It will not always be staggered. Sometimes you'll be drawing the next one of these that we'll do will be eclipsed. So you'll see how that goes. But just copy paste, right? So H, want to be inorganic chemistry. You can have, in a sense, miscopy error. So you do have to be alert and have your widths value as you copy this over to make sure after all that work that you just copy over your answers accurately. It would be a shame if you did all that work and you miscopied it here. It does happen. And that's what this person is looking at as the stick person looks down that bond axis. At that point in time, the molecule appeared to that person like that. At that split instant, this molecule appeared like that. So this is called if you want some advanced information, a staggered conformation, because nothing's being eclipsed or hidden. Okay, so nothing's being eclipsed or hidden. So I will hold off on doing the other one. I may assign that for later. I'll find out if in any event that happens. And the next sheet, you see, I used to teach this during lecture, and then the lecture periods got cut from 60 minutes to 50 minutes. Thereby, I lost over 2.5 weeks of class, and this was one of the topics which got cut, and it's now relegated to a film lesson, which I hope I'm doing a good job on. So the rest of this portion of film 2 will take us to the end of the page here. Okay. So we'll do 1, 2, 3, 4, and then I'm going to do 5E, and then we'll cut the film there. So this used to be, once again, a nice handout to get students acclimated to Newman projections. A very nice, thoughtful worksheet, which I'll do with you now. Represent the front carbon in the number 1, please. Represent the front carbon in a Newman projection. Is it a spoke or a sphere? Front carbon, spoke, we have learned. It can be drawn like the letter Y or an inverted Y. Represent the back carbon in a Newman projection. That's a sphere, and it can be drawn spherically, analogously, 2 up, 1 down. And by the way, these pegs should be shorter, or 1 up and 2 down. And that's number 1 and 2 already. Number 3, report the total number of carbon atoms in each Newman projection. So I'm going to draw arrows to them. I already got a head start on you. So there's 1. And I'll give you moments to think about this. How many in quantity? 7, 2, 9. How many carbon atoms are in each Newman projection? So this is good. So if you get this answer correct, you should feel good about yourself if you got this answer correct. Okay, let's talk about this. So there are 2 different ways to show a methyl, CH3 or an endpoint. So that's another carbon there. So these are both methyl CH3, CH3. By the way, this is a carbon. This is what we call the spoke. And lastly, we have the sphere. So in all, we have methyl, methyl, spoke, sphere. And this makes 4 carbon atoms in that representation. Good to know. And with that information in hand, maybe that'll make answering B, question number letter B, better for you. So I'm going to start out here. This is an ethyl group. Vertex endpoint. Here we have an isopropyl. Vertex endpoint. Here's another endpoint. And we have a spoke and a sphere. I believe that's it. And I will now type this out. Ethyl, vertex, endpoint, 2 carbons, isopropyl, vertex, endpoint, for 3 carbons, and the spoke and the sphere. 7 carbons, if math is good, 7 carbons. Back when I used to teach this in lecture, I used to make however many models, 44, 50 of these models for students. So and then I would have them do this practice. So I'm gonna do this with you and stop sharing at this time. If you have a molecular model kit, I would make your molecular model so that you have a red vertex nugget and a black vertex nugget. The red vertex nugget holds a blue piece of plastic, and the black vertex nugget holds a white piece of plastic. So, and they're both pointing down, or are they not? I'll do my best here to present this to you. All right, that's better. Hold the molecular model so that the colored vertex, I'm holding it, is to the left. And the carbon vertex is to the right. Rotate the bond so that the colored sphere, the blue one, is up. Rotate this molecule by hand so that the color vertex, the red one, is closer to you. And the carbon vertex, the closer is the spoke. The carbon vertex is in the back, the sphere. The black carbon vertex is in the back, the sphere. The colored vertex, colored red, is in the front, the spoke. The carbon vertex, the back, is the sphere. The red is more toward you. In the front toward you. Draw what you see. At this point, I would draw a spoke with the blue atom up and a sphere with the white atom down. Spoke, blue atom up, sphere, white atom down. All right, I'm gonna go back to the draw capabilities. Try to present that for you. It's really better when done in person, but that's so it would look kind of hack if I just skip this. So it's just really, it's meant to be done in person. So I apologize. So what I was going to draw here was the whoops, I did that wrong. So spoke with the blue atom up. That means it's an inverted Y. I'll just put blue here. Blue atom. And the sphere with the white atom down. I have to go back and put in the little marks there. goes in there like that. So that's what you saw at that point in time. And here it is again. Newman projection bears that out. Blue atoms up, white atoms down upon doing all that. So it was an exercise. Well, why was that exercise there? That was just to reconcile, allow students to reconcile that doing that this molecule is the same as this molecule. That this molecule is the same as this molecule, but from a different point of view. And now I want to skirt down to number 5. We've seen these before. The stick person's not here. Now we have this type of icon says view. So I like to try E because this is going to end up a little differently than we've seen before. So, all right, so let's arrange a table. Doesn't take long. You can arrange your own table. So group and up or down and left or right. We're doing E because this is going to give us an eclipsed conformation, which I would like you to be able to draw. Group, got the H and NH2. See, this time we're not so lucky. We have to make a choice here. Here we have methyl on the back. This is the sphere, a hydrogen, and this is what's called a vinyl group with a double bond. Okay, let that be called vinyl. I can even help us out a bit. Spoke, if room allows, and whoops, and the sphere. Oh, just barely, but barely. We're looking, so give yourself some chance to get used to the presentation here. Okay, we're looking at that. Whoops, we don't need the letter E, do we? So I'll try to cut that out. But that's the data that you're analyzing, and you're trying to assemble this into a table, and then from the table hoist that into the Newman projection. My glasses can come off, and I can put my face flush to the screen. The screen is pretty hot on my cheek. Okay, so and you remember about the layering with the blue laser? It goes wedge, blue laser, hash. So from the person's point of view. So I've given you, I've turned the toolbox upside down and shaken everything out. This is all I have to help you understand that. So here we have another good example for you. So the hydrogen, isn't it more up? Has a high altitude, right? Based on this arrow here, the hydrogen has a high height. Up. Is it to the left or right? Neither. How about the NH2? It's more down. What's higher in height? Hydrogen or NH2? Hydrogen's higher than NH2 in height. In height. And if I take off my glasses, put my cheek next to the screen, my cheek is very hot. And understanding what I know about wedges and hashes, the NH2 is to the, I hope you got it correctly, it's to the left. And that makes this one down and to the right. So right now, I already know that I'm going to be using up, down, down, correct? UDD, up, down, down. Which spoke satisfies? It's this one. I have H here. All directions here, down and to the left, NH2. And down and to the right, methyl. Partial credit building. And it goes on for the sphere. Methyl, again, is up. And it's neither. See how this is going to give an eclipse conformation? Hydrogen. You can use your answer from before. The NH2 was on a hash, so is hydrogen here. The point of view has not changed. Still the same, so therefore this is the hash will give a left. And the double bond moiety, that would be down and to the right. So we have again up, down, down, UDD, up, down, down. Which sphere is best here? It's this one. Fill it in, please. Methyl is up. And we have the hydrogen down and to the left. And the vinyl, I can put VN here to the down to the right. So let's try to assemble a Newman projection here. So why don't we draw, this is the total answer here. Total answer. Superimpose. It's going to get crowded because this is going to be an eclipse conformation. I shall do my best. Vinyl. That's our, thankfully I copied it correctly. It does take some level of attention to copy over correctly. So, and I'm going to make, in this case with eclipse conformations, I'm going to make the spoke bonds markedly longer. It doesn't matter if the spoke bond is to the left or the right of the sphere. So, ooh, I missed that one. I don't want to write over that. So, and so I want to take this stuff and copy it over now accurately, having to pay attention here. Hydrogen, NH2, yeah, to the left. And methyl, you want me to write ME to the right? You know, I could be smart and just leave that there, but I will try to cram in methyl here for each and every one of you. So here we see an eclipsed conformation. An eclipsed conformation where this atom is kind of difficult to see. That atom is not as easy to see. Right now you can't see it. It's eclipsed. This is an eclipsed conformation. I can't see that too well. And this conformation is not as stable. It is allowed to exist. So nothing with respect to octet role is happening. It's allowed to exist. It's perfectly permitted to exist by nature. But on the whole, compared to other shapes, this shape is more unstable, has a higher energy, has more pent-up energy than other shapes, this eclipse conformation. So that's what the rest of this activity is about. So we'll drive down and do these examples here and bring this Newman projection business further along. So that's it for film 2, and film 3 we'll get into the definitions and choices as to which shape of a molecule is more stable than the other shape. See you then.